In this lecture, we are going to see about the plane diffraction grating and the grating which we use in the lab. We can see here, and when come to the definition, this we can define as an arrangement consisting of a large number of parallel slits of equal width and separated from each other by opaque spaces is called a diffraction grating. So one part is a transparent in the middle, and as a line we can see it's a opaque surface. So basically a grading is made by ruling a large number of fine equidistant and parallel lines, as we can see in this figure, with a diamond point on an optically plane glass plate. Now in the present lecture we are going to analyze how this plane diffraction grating works. So in order to understand that, whatever we studied previously, single slit diffraction or double slit diffraction, that information we can use here. So here we will assume a large number of parallel slits of equal width separated from each other by equal opaque spaces. The total width is A plus B, and here what we assume is, without deviating, rays are focused at C, and with a deviation of theta they are focused at P. Finally, what we are supposed to get is, we have to get the intensity. So in order to get the intensity, we have to get the phase difference. For the phase difference, we required a path difference. Here we have a grating, a lens and a screen. These are the things we required for the analysis purpose. It is a N-slit diffraction as well as plane diffraction grating, we can say. Here we will consider a single slit, and its amplitude we can write directly A sin alpha by alpha. Then we will consider the contribution of remaining slits, and we will summarize the thing. Then from Fraunhofer diffraction at single slit, we assume as a single slit, all secondary waves proceeding from slit in a direction theta are equivalent to a single wave of amplitude. So this one we used in single slit diffraction. R is equal to A sin alpha by alpha, where alpha is equal to pi A sin theta by lambda. Then the path difference between two successive waves. So as we did in single slit, the same pattern we will get A plus B sin theta. Then the corresponding phase difference will be 2 pi by lambda into path difference. That's why we will get 2 pi by lambda into A plus B into sin theta. That we will assume as 2 beta. In order to find the amplitude, that's what we are supposed to do. Once we calculate the path difference, next phase difference, then amplitude. So in order to find the amplitude in the direction theta, we have to find the resultant amplitude of n waves, each having amplitude r and common phase. So using a standard results, we will write r prime is equal to r into sin n beta by sin beta. R we already know that we will replace with r is equal to a sin alpha by alpha, where this a is nothing but small n a. Then the resultant intensity at a point P is given by square of the amplitude. So when we do the square, it will become a square sin square alpha by alpha square sin square n beta by sin square beta. This one we will draw as an intensity distribution curve. First principal maximum, that second is a second principal maximum. Like that we can get the intensity distribution here. Then we are going to see about the resolving power of a material. Resolving power. So what do you mean by resolving power basically? So resolving power is, what we can say is, it's an ability of an optical instrument to just resolve the images of two nearby point sources or objects is called its resolving power. Here we can see, here 2 points are there. They are separated, they are near, but they are well resolved. It means that we are able to distinguish between these two. But in the second image, we can see they are just resolved. In the third image, both are completely overlapped. So here we cannot distinguish between 1 and 2. Combinedly they look as a single one. So it's a well resolved, just resolved and a not resolved. Now we will come to Rayleigh criteria. So the 2 point sources or 2 spectral lines of equal intensity are just resolved by an optical instrument. So when a central maxima of a diffraction pattern due to 1 falls on the first minimum of the diffraction pattern of the other. So here two things are we have to consider. One is the central maxima of 1, and second one is first minima of the another spectral line. If they are overlap, then we can just resolve it. So in order to understand that one, they consider a 2 spectral lines having wavelength lambda and lambda plus d lambda. We can see here, this is the principal maxima. This principal maxima is overlapped with the minima of that lambda plus d lambda. This is a central is theta. This is a 3 theta prime. So in the next case, there come little closure. So they get overlap and a dip they will created here. Reduction in the intensity. In the third case, they completely overlap and form a resultant intensity. So in those scenarios, we calculate the resultant intensity. We can identify whether they are completely resolved or not. If the resultant intensity, whatever we calculate basing on this one, resultant intensity is more than 81% of either maximum. Here, we have a lambda and lambda plus d lambda. If we can take any one, if the resultant intensity is more than 81% of either maxima, then it is not resolved. Then if the resultant intensity is equal to 81% of either maxima, so if it is 81%, then we can say it's a just resolve. Resultant intensity is less than 81% of either maxima, then it is fully resolved. Next one is we have to find out resolving power of a plane transmission grating. So in order to find the plane transmission grating, we use a Rayleigh criteria. So according to Rayleigh criteria, we have to identify the position of principal maxima and its first minima adjacent to the principal maxima. From there we have to calculate. So how we can define resolving power? Resolving power of a grating or optical instrument defined as it's a ratio of the wavelength of either spectral line with the smallest wavelength difference in two close spectral lines. For that purpose, what we will do, we will consider a beam of having two different wavelengths, lambda plus d lambda, and we will apply Rayleigh's criteria. In order to get that one, we have to take a source from where it is coming, slit simply, then a collimating lens. It will make the beam into parallel beam, and then this is a AB is nothing but a transmission grating. Once the light is transmitted, then we will use another lens which will converge onto the screen, converge the light onto the screen. So here it will forms the maximas and minimas. So the direction of n principal maxima is given by a plus b sine theta is equal to n lambda. So this one we can take from the grating directly. Then the direction of minima is given by n into a plus b sine theta into m lambda. This is the nth principal maxima. This is for minima. N into a plus b sine theta into m lambda. Capital N is that's a number of the slits. So where m can take any integer values except 0, n, 2n, 3n, nn. The first minima adjacent to this nth principal maxima in theta increasing direction, it is theta plus d theta with m is equal to nn plus 1. N is the order of the grating, capital N is the number of the slits as 1. Now what we have to do is we have to just substitute here in the place of theta, theta plus d theta, and in the place of m, n plus 1. So this one we will treat it as a equation number 1. For just resolution of a spectral lines lambda plus d lambda, nth maxima of n plus d lambda and first minima of lambda should be formed in the same direction, that is theta plus d theta. So that is given by nth order maxima, that is a plus b sine theta plus d theta is equal to n into lambda plus d lambda. So if we multiply with capital N on the both sides, capital N is nothing but number of slits. The two equations, that first equation and second equation, left hand side will be same. So in the first equation it is n into a plus b sine theta plus d theta, and here also it is n into a plus b sine theta plus d theta. So whenever the left hand sides are equal for both equations, we will equate the right hand sides. So whenever we equate the right hand sides, we will get this expression, and on simplification, we will get lambda by d lambda is equal to n into n, equal to n into a plus b sine theta by lambda, where small n is the order, capital N is the number of the slit. So the resolving power of a grating is product of the order of the spectrum with the total number of the lines on the grating. You can identify the resolving power of a grating by using this formula.